Alright, so this is take two. I don't know, for some reason the first video didn't have any sound, so let's try this again. Alright, we're going to perform some transformations on quadratics. Now, the goal here is to recognize, using function notation, what transformation is being performed on a quadratic. But really what we're trying to do is recognize, as the equation changes of a quadratic, its graph will also change. And conversely, as the graph changes, the equation changes. So let's work with f of x equals x squared. What would happen if we had f of negative x? So using function notation, I should recognize that the x value is being negated, which means that it's a reflection over the y-axis. Now, if I found the equation of f of negative x, that's asking me to plug in negative x for x here, so we get negative x squared. Let's draw both of these graphs and see what happens. So x squared looks like that. It's a parabola. And if I reflect this over the y-axis, so this is y equals x squared. If I reflect it over the y-axis, it is its own image because the graph is symmetrical about the y-axis. So that is the graph of y equals negative x squared. F of x equals x squared again. Let's see what happens if we have negative f of x. So negative f of x is asking me to put a negative in front of our function, negative x squared. Notice the difference in notation here. These mean completely different things. The order of operations here says to make your x value negative and then square it, where the order of operations here asks you to square and then make it negative. So this is giving me only negative output values. So using function notation, I should recognize that this is asking me to negate my y value, which means it's a reflection over the x-axis. This is the graph of y equals x squared. And if I reflect that over the x-axis, this is the graph of y equals negative x squared. Now let's do one more reflection here. Here is the graph of f of x equals x squared. What about f inverse of x? Well, that's going to take a little bit of side work. We have y equals x squared. Let's interchange x and y. Take the square root of both sides. But don't forget, the square root can be both positive and negative. So our inverse is both positive and negative radical x. Now we know that graphically, this is a reflection over the line y equals x. So our graph of the inverse will look like that. And that is the graph of y equals positive and negative radical x. Let's do some translations now. If we were to translate y equals x squared, let's find f of x minus 2. Well, that's asking me to plug in x minus 2 for x. So that's what the equation would look like. But using function notation, I know that this is a translation of 2 in an x direction and 0 in a y direction. Let's draw the graph of y equals x squared. And if I translate this 2, I'm moving to the right 2 units. So this vertex right here would end up right there at x equals 2. So this is what my new graph would look like. And this is the graph of y equals x plus 2, sorry, x minus 2 squared. y equals x minus 2 squared. Inside of the function means x direction, but opposite direction. Now, function in this case means whatever the equation is asking you to do. The function here we're working with is something being squared. So the minus 2 is before we square it. Let's translate in a vertical direction. Let's find f of x plus 3. Well, that's just asking me to add 3 to my f of x. X squared plus 3. Using function notation, I should recognize that this is a translation of 0 in an x direction and positive 3 in a y direction. Now, outside of the function means after I square something. Inside of the function, before I square it. Outside of the function, after I square it. So the graph of y equals x squared looks like that. And if I translate this up, my vertex here, which was 0, 0, is now at 0, 3. And here is the graph of y equals x squared plus 3. Just a couple dilations. Here's x squared. Let's see what happens when we multiply our function by 2. This is y equals x squared, and a dilating factor is asking me to multiply all of my y coordinates by 2. So I'm going to have to choose some ordered pairs from this graph and see exactly what happens here. Here are 5 ordered pairs for y equals x squared. This is the ordered pair 0, 0. This is the ordered pair 1, 1. And this is the ordered pair 2, 4. This is the ordered pair negative 1, 1. And this is the ordered pair negative 2, 4. So I'm going to multiply all of these y values by 2. The x values aren't changing. So 0 times 0 times 2. The y value here is 1. Multiply it by 2. 4 times 2 is 8. 1 times 2 is 2. And 4 times 2 is 8. So here's the shape of my new graph, y equals 2x squared. And notice how it made the graph more narrow. It stretched it towards the y-axis. F of x equals x squared. What happens if we multiply a number smaller than 1? Let's draw the graph of x squared. And then we're going to do the same thing we did up here. We're going to list some ordered pairs and multiply their y values by a half now. So if 0 is my y value, multiplied by half, it's still 0. If 1 is my y value, multiplied by a half. If 4 is my y value, multiplied by a half. And this graph is symmetrical, so now we have a graph that looks like this. 1/2 x squared. So to summarize dilations, for any function y equals ax squared, if a is greater than 1, makes the graph more narrow. If a is between 0 and 1, makes the graph wider. Now notice how it didn't include negatives, because then it would be a reflection.